Chapter 3, Operators. C has an extensive set of operators, and they can nicely be put into 5 categories: mathematical, relational, logical, bitwise, and assignment. The first 3 are pretty much what you expect, the usual arithmetic, addition, multiplication. There's actually a couple of operators in there that are pretty useful that you won't find in other languages, though. Then there's the usual relational operators and logical or truth value operators. And then the next 2 categories, the last 2, are quite unique. Not too many languages have bitwise operators, but again, that's because of C's heritage as a system programming language. So there are operators to shift bits around and to flip them and things like that. And the assignment operators, as you'll see, are also quite unique. They allow you to make an assignment to a particular variable, for example, to add something to a variable with less code than you're used to. And the last thing that we'll look at is how these operators fit into a hierarchy of precedence and associativity. As in all computer languages, the operators in C are either unary operators or binary operators. Unary operators like negate, to give back the negative version of a number, say. Binary operators are the usual ones for arithmetic, and such others, but there is an exception. It's quite interesting. There is a ternary operator, one that has 3 operands. Therefore, there's 2 symbols that make up that operator, the question mark and the colon. Sometimes it's called the conditional operator because it pretty much behaves like an if-else. So if you look at the example here, it says max equals, and then that first portion, that first operand which precedes the question mark is the condition. X greater than Y. If that is true, then the next operand is the value that is returned from this expression, X. Otherwise, if it's not true, then Y is returned. So this is pretty much logically the same as if X is greater than Y, max equals X, else max equals Y. However, it's a more compact statement. I'll admit that you might find it a little cryptic at first, but it also is likely to generate less code. And so again, when you are in situations where efficiency really matters, then this is the thing to do. There are also other times when you want to have an expression which returns a value or another, but it's embedded within another expression. Therefore, you really can't use the if-else in that situation. And so that is when this ternary operator is very handy. The mathematical operators include those for addition and multiplication. And you'll notice that in addition to the usual ones, plus and minus, say, for the additive type operations, there's a couple of strange ones, plus plus, minus minus. These are the increment and decrement operators. And there are actually 2 versions. That is, you can use these operators, and they are unary operators, as a prefix or a postfix to an expression. So to illustrate, the first line there says I equals j++. Well, what that means is take the current value that is in j, store that into I, and then as a side effect, after the assignment has been made, then increment j. So it's essentially the same as I equals j, j equals j plus 1. But it's faster. And again, such an expression can be embedded within another expression, which is pretty common in C. The prefix version increments first and then gives you the incremented value back as the return value for that expression. So in the next line, I will actually get the incremented value. Multiplicative operators, there's the usual multiply and divide, but in addition, there's the modulus operator. If you know Pascal, then you've probably used the actual mod operator, MOD. Well, this is equivalent to that. So the percent sign, when used as a binary operator with 2 integers, gives you the remainder of dividing the first one by the second. The relational type operators include equality, inequality, and then the usual comparison, greater than and less than. And the main difference is that equality is not a single equals sign, but a double equals sign. And that's interesting. That sometimes causes some unusual errors. For example, what you should do when you're testing for equality is you should say, as in the first line there, if I equal j. But if you're used to using other languages, it's pretty common to just say if I equals j. And that is an error. However, it's a logical error. The compiler is not going to catch that. Because what happens is, in the second example, j will be assigned to I, and then the result of that expression, which will be whatever value was put into I, will be evaluated as a truth value. And as we'll explain on the next slide, non-zero values, when evaluated in a Boolean context, are true, and 0 is false. And so what the compiler is going to do, here in this case, it's going to say if, and then whatever value was in j, which in turn is assigned to I, if it's non-zero, it's going to be true. And if it's 0, it'll be considered false. So you really got to watch out for that. That is one of those unusual things in C. Java doesn't have this problem, but you do in C and C++, so watch out. Inequality uses the exclamation point and equal instead of the less than, greater than, as some other languages do. There is no Boolean type in C, like there is, say, in Pascal or in C++ or in Java. And so anything that is evaluated for a truth value is just considered as a number, generally an integer. And so if the result of some expression, no matter how complicated, is a 0, then it's considered false. And if it's a non-zero, it's considered true. There are logical operators that allow you to construct fairly complex Boolean expressions. They're the usual connectives, and, or, and then not, which of course negates the truth value of an expression. The and is a double ampersand.
And it has a usual feature that is,
both the and the or, the connectives, have an unusual but very useful feature. It's called short-circuit Boolean evaluation, and it's illustrated in both of the examples that are here. So in the first example, it says if I is less than n and a sub I equals 99. Well, if it turns out that the first expression, I less than n, is false, well, that's sufficient to determine the truth value of the entire compound expression, because false and anything else is false. Therefore, it won't even go on to evaluate the second expression, a sub I compared to 99. And that's pretty useful, because that allows you to test an element in an array without worrying about going beyond the bounds. Because if n is beyond the bounds of an array, you don't want to say a sub n, because that's accessing outside of an array's limits. So it's a pretty handy feature. But likewise on the second one, it's a silly little expression, I realize, but if I is equal to 2, well, that's sufficient to determine the truth of the whole thing. And so it doesn't even go on to evaluate the second expression, I compared to 3, and so it's more efficient. Nice feature. Not is simply the exclamation point. The bitwise operators allow you to fiddle with bits, of course. The and, the single ampersand, what it does is it allows you to take two numbers, and if you and them bitwise, it'll go through each bit position, the corresponding bit positions in the two numbers, and if both of them are 1, then the corresponding result in the output number of the expression will be a 1, otherwise it'll be 0. Or is the inclusive or. Either one or both is a 1, then the result will be 1 for the expression. Exclusive or is one or the other, but not both. One's complement just flips all the bits in a number, and the shift left and shift right do what you think they do. The next slide has an example. This example takes a couple of numbers and exercises the bitwise operators on them so you can see how they work. And I've included in a comment there the bit patterns for those two numbers. The first example, first operation, is in that first printf statement. It's going to print out the result of the bitwise and of the two numbers. So if you take a look, you would expect only 3 bits to come out in the answer, because there's only 3 bit positions that are 1 in both numbers. For the inclusive or, the vertical bar, you would expect 6 to come out. How about the exclusive or? Well, you look for those where there is a 1 in one of the numbers, but the corresponding position in the other number does not have a 1. And so if you take a look at that, there should be 3 bits that come out in the answer. the twiddle there, or tilde, whatever you want to call it, of course, just flips all the bits. And to shift bits left, which is what the double less than does, we'll just take your number and shift it left 3-bit positions. So all of the bits are just moved down to the left that many positions. And as you fill in from the right, it'll just give you zeros. When you shift to the right, it'll do the same thing. It'll move all the bits 3 positions to the right, but it will fill in the sign bit of the number. We're actually not going to worry about that. I'll cover that in greater detail for those that are going on to C++ in Chapter 9. So the output's on the next slide. Oh, before we leave this one, notice the format in the print statement. It says %04x. Well, x is hexadecimal, and so it's going to print the values out in hexadecimal. That's just for convenience, so you can compare them to the binary bit patterns that you expect. And the leading 0 in that 04 says that I want it to print it out with leading zeros. So we expect these hexadecimal numbers to be printed out in fields of 4 with leading zeros as necessary, and that's exactly what it does. Here's the output from the previous slide. You can see that it is being printed in hexadecimal with leading zeros. I've put the bit pattern off to the right. So if you want to go back to the previous slide and compare and make sure the right answer is coming out, you can do that. Notice, though, I do have something a little unusual with the complement, the twiddle in. Instead of just printing out 4 digits as I asked for, I'm getting a lot more. I'm getting 8. Well, if you'll recall, whenever an integer value is involved in an expression, it is always promoted to either an int or a long as necessary. And so here what I have is I have a short int having to be promoted to a full int, because that's the way it is. And then when I flip those bits, I've got significant values up there in the most significant 2 bytes of that number. And so the system is not going to drop those in the output. So it prints out the full 8 hexadecimal digits. If I want to actually truncate those and ignore them, because I want everything to be just 4 digits, I can do that with the format. And that's down at the bottom there, the printf statement. You just add an H before the X. H stands for half word, and so that's what is used for a short. And that will truncate the top 2 bytes. Any of the binary operators in C can be used in a special assignment version, which is really quite convenient. Take a look at the bottom line of the slide for an example. I've written I plus equals 5. That's logically the same as if I had said I equals I plus 5, with the added benefit that it very likely will be more efficient. It will generate more efficient machine code. And furthermore, I could take this expression and embed it inside of another. So, this is a very powerful concept that C has, allowing these expressions to be embedded within others. You do have to be careful, though. C does have a reputation of being a cryptic language, and some people go overboard and do the most complicated expressions they can, and while it may generate more efficient machine code, it's not readable by hardly anybody. Kind of a write-only type style of coding. But it's pretty common, at least in simple assignments like this, to use the assignment version as a shorthand for the full traditional statement. When you have more than one operation in a statement, you need to know how they associate. In other words, what order those operators will actually be executed in. Most operators go left to right, which is what you would expect, but there are some operators that just don't make sense doing that. For example, the assignment operators. If you say I equals J equals K, well, it really is more intuitive to think of that as going from right to left, and that's the way it works. And so all of the assignment operators, including the ones on the last slide where you combine them with binary operators, they all work that way. They associate right to left if you have more than one of them in adjacent positions in the same expression. Everything else, of course, goes left to right as you would expect. So I plus J plus K, I plus J will be evaluated first, and then that result will in turn be added to K. Another important aspect of operations that you need to keep in mind, of course, is their precedence or priority. Some operators are higher priority than others, And so if they appear in context with other operations, the higher priority ones will be done first. And this follows the mathematical intuition that most of us have. For example, if I say A plus B times C, I expect the multiplication to be done first. That's the way we write it algebraically. So therefore, multiplicative operators have pretty high priority. The unary ones do too, and that's to be expected. So kind of the rule of thumb is the unary operators are right up there on the top, and then the order after that will kind of go according to your mathematical intuition. The multiplication operators will be next, and maybe the addition operators. And down on the bottom will be the assignment operators, because usually the last thing you want to do when you've calculated some complicated expression is to assign it to some variable. Now, if you really, really want to know what the precedence is for each operator, you're just going to have to look it up. It's not something that lends itself to a conversational exposition like we have here. So just look that up in any book or in your manual that comes with your compiler. But do keep in mind the thing that is in the fourth bullet there. It's very difficult to fit the bitwise operators inside the context of all the other operators in an intuitive way. Sit down and try to do it sometime. It's just not that easy. And so they have kind of strange precedence. For that reason, the rule of thumb is when in doubt, always use parentheses when you have bitwise operators. Otherwise, you'll have some surprises. Probably the key things to mention as we summarize here is that C has the usual operators that you would expect with some additional operators and also some exceptional things. For example, I mentioned that there is that ternary operator. That's quite unusual. The modulus operator is the percent sign. One thing that you really got to watch out for a lot is the equality testing. Always remember two equal signs. I guarantee you're going to make that mistake at one time or another. And as I mentioned before, the compiler's not going to help you much. The other thing that's quite different in C is the fact that it doesn't have any Boolean type. And so just remember 0 is false, non-zero is true. As far as how operators group, it's really quite intuitive. Unary and assignment operators group right to left, everything else left to right. But finally, beware of bitwise operators. They're funny. For this exercise, I'd like you to read 3 integers from the keyboard and keep track of which are even and which are odd as you go. So you'll read in a number and test it, whether it's even or odd. And if it's even, you'll add that to a sum of even numbers, and if it's odd, you'll add that to the sum of the odd numbers. So this is just a little exercise in not only doing input, but using some of the operators, including bitwise operators, and getting used to the precedence. When I say bitwise, I guess I'm kind of giving away how to do this. How do you know if a number is even or odd or not? Well, you probably know how to figure that out, but the easiest way to do that is just any number mod 2 is going to yield a 0 or a 1. If it's 0 mod 2, then it's even, otherwise it's odd.